The ones we looked at yesterday involved isolated systems, for the most part, where mechanical energy is conserved. An isolated system is a system where there are no outside forces acting, so there's no friction, there's no monkey running along beside the block of wood adding energy to it. It's just happening on its own. If there are no outside forces present, that means the total amount of mechanical energy in the system cannot change. So when I say EKI plus EPI equals EKF plus EPF, all I am telling you is that the energy in the system at one point in time happens to be exactly equal to the energy in the system at some later point in time. That's conservation of energy. That's what you're doing. So knowing maybe how fast an object is moving to begin with and how high above the ground it is, you can calculate how fast it's moving later if you know how high above the ground it is later. And the nice thing about this is this has nothing to do with vectors or directions. So if I tell you, this is an interesting question, I tell you that an object is launched from the ground at some particular angle, and it's launched at 22 meters per second, you can answer the following question without using kinematics or two-dimensional motion. How fast is it? How fast is it moving at a height of 10 meters? Like, this is a very complicated question to solve if you're going to use projectile motion. And by the way, you would need to know the angle, and I'm not even telling you what the angle is. So what you would do is you would say, well, contrary to how I drew it, the ball is not hovering. It has no height to begin with. And all you're told is 22 meters per second and then a height of 10 later on. Well, you can say that initially there's kinetic energy, but there's no potential energy because it is at its lowest point. Afterwards, there's kinetic energy, and there's potential energy due to gravitational forces acting on it. This becomes 1/2 mv squared equals 1/2 mv squared plus mgh. You can cancel the masses, and you can solve for the speed. And nowhere did we ever talk about in this solution, and I'll finish it in a second, nowhere do I talk about a horizontal component or a vertical component. Although this is a vertical component, it doesn't matter. I'm going to multiply both sides. No, let's leave it as 1/2. 1/2 times, what did I say? 22 meters per second. We have to square that. Equals 1/2 times the speed later squared plus 9.81 times 10. You can solve that. Like, think about that. If I gave you this question in the first unit with projectile motion, everybody would go, well, I can't solve it. What's the angle? Because you would need to know the angle. And then, even then, it would become quite complicated. I hope I chose a height that's going to work. Do you see that I'm going to have to take 1/2 times 22 squared and subtract this number here? Had I chosen a height like 200 meters, when you subtract it, you would get a negative, which means it never reaches that height. Okay? But I chose a relatively small height. This would be 0.5 times 22, and I have to subtract 9.81 times 10. It is negative. Oh, I forgot to square. My mistake. I forgot to square the 22, didn't I? There we go. And that's equal to 1/2 times v squared, so I would have to multiply that by 2 and then take the square root. So the answer is, when it's at a height of 10 meters, it will be moving at 17 meters per second. Energy as a idea in physics makes a lot of problems simpler to solve. Forces are useful, but energy is simpler. All that being said now, does anybody have any questions you would like me to go over from this section? Go ahead, Nate.
Number 6.
Okay, let's look at number 6, please. So a pendulum is dropped from the position shown. What is the speed of the pendulum as it passes the equilibrium position, which is going to be the lowest point? We've talked a couple of classes ago about equilibrium position simply being where things end up if you leave them alone long enough. So my thinking here is to say that h is 0 here at the lowest point. And by doing that, what I'm saying is gravitational potential energy at that point is 0 because it's the lowest point. And you could argue that if the string broke, it's not the lowest point. Right? The floor would be the lowest point. But this makes our calculations easier. What that means is that at the highest point, the height of the pendulum is 0.25 meters. And it also means that at the lowest point, there's no potential energy. So what we can do is say the mechanical energy at the top has to equal the mechanical energy at the bottom. And now we start, with a magnifying glass looking at a little more detail to this. When it's at the top, that's the point where I pull it back and I let it go. So when it's at the top, at that instant that I let it go, there's no kinetic energy. So this will just be gravitational potential energy. And I'm in teaching mode right now, and you're in learning mode. I'm just writing MGH. If you were doing a written response somewhere, you might write EP, and then in the next step, put MGH. When it reaches the bottom, it's not moving at all, or it's moving at the bottom, so it has kinetic energy. But at the bottom, it's at its lowest point, so there's no potential. So this is going to equal at the bottom, the mechanical energy will all be kinetic. Like mechanical is kinetic plus potential. But at the top, there's no kinetic, and at the bottom, there's no potential. The masses cancel, and you can go ahead and solve this problem. We can take 9.81. Personally, I would multiply both sides by 2, and just as an alternative method, write 2gh equals v squared, but you don't have to. Okay. 9.81, I'll leave the units out for this, times 0.25 equals 1/2 times v squared. And we can solve that. 9.81 times 0.25, we're going to have to double that because of the half. Thank you. And then we're going to have to take the square root. So this is the answer. Is that okay? Now I want to point something out to you. Nowhere in this question did it direct you to use h equals 0 at the bottom. Right? So imagine, I don't know how else you would do it, but imagine you said, geez, I don't know where the floor is. I'm going to put the floor here. Just play along here. I'm going to put the floor here, and I'm going to say that this is 1.1 meters to there. Let's just say that you did that. Or maybe I give you that in the question. If you did that and you used the floor, then the mechanical energy at the top, which is, I'll write it over here so it looks like it's at the top. At the top would simply be mgh, wouldn't it? It's not moving at the top. But your mechanical energy at the bottom would be mgh plus 1/2 mv squared. This is the bottom. Getting a little sloppy here. There we go. Are you with me on that, you guys? Okay. The difference here is for the h at the top, you would put 1.35 meters. Just think about where I'm getting 1.35 from. It's the 1.1 plus the 0.25. So you would have, let's cancel the masses. You would have here 1.35 meters times g, right? And over here, you would have 1.1 meters times g. Are you with me? If you wanted to get v by itself, you would subtract 1.1 times g from both sides. Well, what's 1.35 g minus 1.1 g? It's 0.25 g. That's what we used. This is one of the ways I can explain to you that you were allowed to assign h equals 0 wherever your heart desires. Because if you assign h equals 0 to a higher location, you're just taking away energy from both sides of this equation. And you're taking away the same amount of energy. If you assign h to be at a lower point, you're adding a certain amount of energy to both sides, but it's the same amount. Other questions? Jay? Number 12? Okay, and I just saw a couple of other people nod for that. A 1 kilogram box slides without friction around the loop apparatus shown in the diagram. The object starts from rest at point A. Does yours actually have an A at the top labeled? It does. And the radius loop is 75 meters. What is the speed of the box at point B? I'm assuming point B is the top of the loop or the bottom? Bottom. Well, this whole thing here is there to confuse you. Because what's going to happen, and it's Friday, my brain's not in full gear yet, but this is going to be, see if you can follow along here. When I let this object, this box, slide from A, at A, it's going to have all potential energy. And as it slides down this part of the ramp, its potential energy is going to decrease and turn into kinetic. And if we use the bottom of this as being, I'll make that a little bigger. If we use the bottom of this diagram as being the lowest point, then whatever potential energy it had at A, it will have that kinetic at the bottom. However, when it goes from here to here, some of that kinetic energy is going to turn back to potential. However, again, when it moves from here to here, all of that potential that it took away from the kinetic at the bottom of the loop to get to the top, all of that potential will be back in kinetic. And that kinetic energy is going to be the kinetic energy it has at the bottom. In other words, it doesn't matter that it goes, let me clean this up now, it doesn't matter that it follows this path. The energy transformations that happen can be analyzed by having it follow that path. And this is why we say, everybody, E mechanical at one place equals E mechanical at another place. It doesn't matter what happens in between, because the total mechanical energy is going to stay the same everywhere. You know, it's going to be in flux between how much of it is kinetic and how much is it potential. But you know what it's like? It's like the pendulum. When I drop it from a particular place, you would agree there's potential energy in the system here, right? If I said to you, what's the potential energy I forgot that I moved that table back. If I, well, now you're awake. If I drop it from here, there's potential energy here, right? If I say, I'll do it this way. If I drop it from here, there's potential energy there. You can't really see it, but it's under the table. And I say, what is the potential energy here? It's the same number, isn't it? We don't care that what happened in between was the potential decreased to zero and the kinetic rose to the maximum. We care about the final position. All right. Nobody was hurt. Well, the table, maybe. It's just a table. It's pretty sturdy. I don't think you can see where it hit. Okay, so anyway, Jay and anybody else who is wondering about this, the mechanical energy it has at the top is only potential. The mechanical energy it has at the bottom is only kinetic. Of course, what we're doing is we're saying this is a height of 0. That's why there's no potential at the bottom. And since it's from rest at the top, there's no kinetic at the top. This question is no different in an analysis than the question Nate asked about. It's going to be mgh at the top equals 1/2 mv squared at the bottom. We can cancel the masses. Look, we don't have to because you're given the mass, but you're not always going to be given the mass, everybody. Sometimes you will not know the mass. And if that's the case, you will be able to cancel them. I'm a big fan of multiplying both sides by 2. And I think you can do the rest even just on your calculator. Take 2 times 9.81 times 2 meters. And then take the square root of that, and you're going to get somewhere between 6 and, well, it's right there, 6.3 meters per second. Any other, is that okay, Jay? Any other questions? All right, we're going to move on today. Today's topic, I'm being ambitious. We're going to try to get through all of the examples today, but it's something we're going to continue working on, I think, on Monday. It requires a lot of practice because things are going to take a turn for the more complicated here. The last lesson was called mechanical energy, and we dealt with conservation of mechanical energy. Here, I'm making this more general, and we're talking about conservation of energy, which could include heat. Heat is a type of energy. It's just that heat is not a type of mechanical energy. We're also going to be looking at something called the WorkEnergy Theorem. So, in the end, after this lesson, you will be able to solve problems where mechanical energy is conserved, which means there are no outside forces. You will be able to solve problems where mechanical energy is not conserved because there are forces of friction producing heat. And you will be able to solve problems where mechanical energy is not conserved because work is added to the system. There is a monkey running along the box, pushing it at the same time. Okay? Warm up. What are the two conditions that can exist if mechanical energy is not conserved? I want everybody to think about that. Well, you don't have to give me two. I mean, just let's start with one. What's something that could be the case if mechanical energy, kinetic and potential, changes? Okay? Friction. There are forces of friction. And again, I want to use the word force with that word. There are forces of friction which produce what type of energy? Heat. Okay. So that's one of them. If a force of friction exists, then heat, which is a type of energy, I know it may seem like I'm nitpicking, but I'm not. Friction is a force, heat is energy. There's a big difference. If a force of friction exists, then heat is created, and what happens in this case is mechanical energy decreases. You end up with less mechanical energy in the system than you had to begin with. And it's not something that's really complicated. If 10 joules of heat are produced, then the mechanical energy has to drop by 10 joules. Okay. Do you have the second one? No? You were thinking the same thing. Will you give me a second situation where mechanical energy would not be conserved? Alex? Energy is added to it. Energy is transferred into the system. Okay, wait a minute. What do you call a transfer of energy? Work. Work is done. And there's nothing wrong with saying energy is added. Let's start with that. I'm going to put in brackets or taken away. Not by frictional forces. But, you know, how can I add mechanical energy to a system? So I have a little toy car rolling down not a very steep incline. It's rolling. And I've trained my dog to grab onto the back of the car and run along at the same time. So my dog would be applying a force in the direction the car is moving. And as the car goes down the ramp, the car will gain speed because potential energy is turning to kinetic energy, but it will also gain more speed, which means more kinetic energy because my dog is doing work. Okay? I hope you can see that what I could train my dog to do is to push the car in the opposite direction, running backwards. It's a circus dog. Okay? And the car is really heavy, so it takes a while for it to slow down. But no animals are hurt. Okay? So energy is added or removed, and what that means is work is done. And don't forget, your head's going to be full of all kinds of things going on here shortly, if it isn't already. Don't forget, work done is just a transfer of energy. You can have a positive amount of work done or a negative amount of work done. If you're talking about energy being added, you have a positive amount of work being done. If you're talking about energy being removed, you have a negative amount of work being done. And the main difference is the force that does the work, the applied force, if the mechanical energy goes up, the force that does the work is in the direction that the object would naturally move on its own, whereas if the force that you apply is in an opposing direction to the motion, you will be doing a negative amount of work and the mechanical energy is lost. Now, I'm going to throw something out here, and if it doesn't stick in your head, that's fine, but I think some of you will appreciate it. A is an example of B. You could argue that A is simply a case where there is an applied force. It happens to be a frictional force, and what it does is it removes mechanical energy from the system, except that it is accounted for in a different way. It's heat. All right? Any questions about those two situations? All right. Oh, look at that. Not going to worry about that. If there is a force of friction present in the system, the force is called a non-conservative force because the force of friction produces heat, decreasing the mechanical energy. Though mechanical energy is not conserved in general, energy is conserved. Is heat part of mechanical energy? No. Mechanical energy is kinetic energy plus potential energy. However, is heat energy? Yeah. Heat is measured in joules. So if frictional forces are present, and let me give you a numerical example to begin with. Let's say that to begin with, and you don't need to write this down, let's say to begin with that you have a mechanical energy in the system of 12 joules of energy, okay? And I tell you, and we did an example like this yesterday, it was our final example in the lesson, and I tell you that the mechanical energy later on is only 10 joules. Is that some kind of mystical magic trick? No. 2 of those joules of mechanical energy were lost to heat because there's some force of friction. Would you agree that the heat here would have to be 2 joules? Okay, well, that's conservation of energy. The energy you have to begin with is equal to the energy you have afterwards. Because when I apply a force of friction, the heat is not there until afterwards. I mean, it's continually being produced as the force is applied. But you don't see the heat or you don't feel the energy of heat before, it's after. And that's all this is saying. The initial mechanical energy before has to be equal to the final mechanical energy plus the heat. Now, if there was no friction, everybody, then how much heat would be produced? There's 0 friction, how much heat would be produced? None. If there was no friction, then this equation becomes this equation, and mechanical energy is conserved, which is what we were dealing with yesterday. Any questions with this idea? Because I'm going to present you with the ideas, and then we have to apply them. So give this some thought right now. Any questions with this idea? Mechanical energy is not conserved, but energy is. There's a difference between saying mechanical energy and just saying energy. All right. Now, I mentioned to you numerous times that heat is energy, but friction is a force. What's the relationship between a force and energy? Well, force times displacement is work. So I'm going to take us back in time here to when we first learned this formula. What force is this formula contain? What does it contain? Is it the net force? What force is it? Aoki? The applied force. And I even said something like, if I want to find the work done by my dog in pulling my garden wagon across my yard, because I've trained my dog to help me in the spring, then I have to use the force applied by my dog. If I want to find the work done by a monkey in pushing a box across the floor, I have to use the force applied by the monkey. If I want to find the work done by a winch pulling somebody out of the ditch, then I have to apply the force applied by the winch. So what is heat? Heat is the work done by a force of friction. Work is energy. Now, this formula is not on your formula sheet. What it's really telling you is that heat, which is a type of energy, is the force of friction times the distance that the friction acts over. So friction and heat are not the same. Heat is what you get for the energy in joules. Friction is the actual force. And I suppose, to boil this down to what's important, you have this formula on your formula sheet, basically. I've told you to ignore the cos theta because I think it can get you into trouble. You have this formula. You just need to know that if you're talking about heat, that's the case. All right. 2, what if no work is done? Or sorry, what if work is done? Well, work is a change in energy. Do you remember me telling you that if I do 100 joules of work to a baseball, the baseball gains 100 joules of energy? So if I had a pendulum, I'm not going to get the pendulum moving. If I have a pendulum and it has a mechanical energy of 10 joules, and it's, what's happening as it swings back and forth is that 10 joules is going from potential to kinetic and back, etc., back and forth. But as it's moving along the bottom, I run along and I do 2 joules of work to it. How much mechanical energy will be in the system then? Well, more. And the idea is that when we first learned about work, we said it was a change in energy, which is final minus initial energy. This is called the WorkEnergy Theorem, and it is actually on your formula sheet. When you look under momentum and energy on your formula sheet, you're going to see the definition of work. It's given as a formula, kind of a formula, but it just says work equals delta E. Let me show it to you. Under momentum and energy, just near the bottom, it says work equals delta E. And you've been taught that delta means change in, and we have to find a change in something by taking final minus initial. Okay, just a second though. If I go back to this, and I say work equals final minus initial, can everybody see that if I add the initial energy to this, to both sides, I get this statement? Okay. If the work done was 0, then mechanical energy is conserved. If it's not 0, then the initial energy is increased by the amount of work done. And if I do a positive amount of work, it goes up, and if I do a negative, it goes down. Now, the only catch to this is some of this final energy could as well be heat. We're going to encounter a situation sooner or later where work is done and that work is adding to the energy in the system, but there's a force of friction taking it away at the same time. But this is the WorkEnergy Theorem. The third case is this. Mechanical energy is conserved. This is if no work is done and no friction is present. So just to cut to the end of the lesson, then we're going to do some examples together. I guess I don't have it here. We won't worry about it. Let's go into the examples. Determine the amount of work done in stopping a train. Okay. Is the mechanical energy of the train conserved when I stop a train? No. Not unless it's being stopped because it's going uphill and then stops at the top and rolls back down. We're assuming here that there's an applied force doing work to the train to stop it. And that means the work done is the change in energy of the train. What kind of energy does the train undergo a change in? Kinetic. It loses kinetic energy. So the work done in this case will be the final kinetic energy minus the initial kinetic energy. Work is always final minus initial. What's the final kinetic energy? 0, because it stops. What's the initial kinetic energy? Well, we can calculate that. It's 1/2 mv squared. That's really simple calculation. The only thing is we do have to convert that 70 kilometers per hour to meters per second. So this is going to be 2.5 times 10 to the 5 kilograms multiplied by 70 divided by 3.6. $19.4 repeating. And we will have our answer. No kinematics, no forces, none of that nonsense. It's just work done is the change in energy. Zero minus 0.5 times the mass, 2.5 times 10 to the 5, times 19.4 squared gives me negative 4.7 times 10 to the 7 joules. That's the work done to the train in stopping it. Lamise, why do you suppose it's negative? Don't know? Kai, why do you think it's negative?
Because you're subtracting. Because it's like in opposite of the momentum.
Right. And I would stay away from the word momentum, though. That means something different than energy and force. Because the train is moving in one direction and the force is in the opposite direction, it's a negative amount of work. Or the work is negative because the train lost the energy. What's the force that did this? Friction. So that means 4.7 times 10 to the 7 joules is the amount of heat produced on the tracks and in all the moving parts when the train stops. And if you knew the distance, you could take that energy and set it equal to the force of friction times the distance and find the force of friction. Number 2, a 15-gram arrow is pulled back 45 centimeters in a bow by exerting an average force of 65 newtons. What is the speed that the bow leaves the arrow at? Well, this is work done. You're doing work to the bow and the arrow by pulling it back. So work done is change in energy. What kind of energy change does the arrow undergo? You're right, but it's not where we want to go with this. The bow and the arrow has no potential energy, and then when I pull it back, it becomes spring potential energy. But I'm going to rephrase my question, Alex. When I release it, what kind of energy change does the arrow undergo? Kinetic. So it has no kinetic energy to begin with, and it has some kinetic energy afterwards. Another way to look at it is that if I pull it back with an average force of 65 newtons, then when I let it go, it will apply forward a force of 65 newtons. And that's where the kinetic energy comes from. So work done is change in energy. This will be final kinetic energy minus initial kinetic energy. This is the force times the distance. And maybe this is the best way to look at it. When I release the string on the bow with the arrow in it, the bow will apply a force of 65 newtons on average over a distance of 0.45 meters. Let's just go a little bit further. Force times displacement equals 1/2 mv/f squared minus 1/2 mvi squared. But this is 0. unless you're running with it when you let it go. But I don't think we want to go that far. So I can put in the numbers, 65 newtons multiplied by 0.45 meters. Well, this is the work done. Newtons times meters is joules. That's how much energy the bow is going to give to the arrow. And it's kinetic, so we're just going to set it equal to 1/2 mv squared. 15 grams. We divide that by 1,000 in order to get the mass in kilograms. And now we can go to the calculator and do some work. 65 times 0.45. I'm going to have to multiply, well, I'll just go equals. This is the amount of energy that the bow is going to give the arrow. Because work done is change in energy. It's giving it to kinetic energy of the arrow. So we can multiply that by 2, divide it by the mass, and then take the square root to get the answer, and it will be moving at about 62 meters per second. So the first two examples deal with situations where work is done. So you go work equals delta E. If work is done, that's what you do. Work equals delta E. Example 3. A rock is thrown straight up by exerting a force over a vertical distance of 1 meter. What's the speed that it leaves the person's hand at? Does the person do work to the rock? Yeah, you apply a force over a distance. So work equals change in energy. This is force times distance. This is final energy minus initial energy. When I'm going to throw a rock in the air, I've got it in my hand, and it's not moving. So it has no energy to begin with. And we're going to assume that in terms of gravitational potential energy, wherever my hand is, that's 0. So this is 0. What kind of energy does the rock have when I let it go? Say it again? It does have potential energy because it's higher than when I started. Yep. mgh. Does it have any other type of energy? Kinetic, because I've accelerated it. What's interesting here is you could have done this question in the previous unit, and I don't want you writing this down, I just want you observing this. But to do it in the previous unit, you would have to say, well, there's an applied force upward. There's a force of gravity downward. You would have said the applied force minus the force of gravity is the net force, which is ma. You would have found the acceleration, dived into the kinematics pool, and pulled out an equation that can be used to find the speed, and done it that way. This is just, I think this is so much cleaner. I don't have to think about directions or forces. Can I cancel the masses? Nope, because there's no mass on the left side. I can take the force times the displacement, 35 newtons. I'm going to leave out the units times 1.1. Was it 1.1? Yeah? 1.1. It's just 1? Thank you. Equals the mass. 2 kilograms times 9.81 times the height that it will be above the lowest point, which is 1 meter, plus 1/2 times the mass, which is 2, times v squared. It's a math problem now. Look, this is just v squared. 1/2 times 2 is v squared. So what you need to do is take 35 times 1 and subtract whatever 2 times 9.81 times 1 is. to say 15.38 when you subtract. So you're going to get 15.38 is equal to v squared. So we take the square root, you're going to get, a little bit, maybe 3.8, 3.9 meters per second. May I borrow your handout for a second, Alex? I'm going to end it there. And I'm going to ask you to turn in your handout to page 44. So I've given you the three situations. Mechanical energy is conserved, which means no work is done, no frictional forces are present. Heat is produced, which means there's a force of friction present. And the third situation is actually this one that we've been dealing with, where work is done. When you take a look on page 44, assignment 2 says, WorkEnergy Theorem, work is done to change the mechanical energy. These are the problems I want you to start working on today. So you have a half hour today to work on that problem set. Then what we're going to do Monday is look at situations where friction is present. Now, I'll warn you, as you get to, how many questions in this section? Does it go up to like 10? 13? I would say up to 8 or 10 for sure. 11, 12, and 13 start to get a little bit more difficult. But we're practicing here with this stuff today, with the work-energy theorem. And then what we'll do on Monday is look at examples with forces of friction producing heat. And we may even spend a third day, Tuesday, on this. I don't know. The way I have it scheduled right now, your unit exam will be Monday, a week from this Monday.